For hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honor and recognition in case of success. This was an ad that Ernest Shackleton posted in a newspaper back in 1914 when he wanted to recruit people to join him on a trans-Antarctic expedition. He had about 5,000 people come out and apply, and he took about 30 with them down to the South Pole. Now the reason I bring this up is because we could see this in our immediate future if we make a trip to Mars. Some mega entrepreneur will put a similar ad in the paper one day, and that ad would look something like this. Men and women wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful. So we have to ask ourselves the key question, why? But most of us don't fall in the category of these intrepid adventurers. So why do we all want to go to space? Well, many people at this conference have talked about existential threats, such as we need to do it because of global warming or nuclear proliferation or fossil fuel shortages, overpopulation, mass extinction events, these kinds of things. To protect the species, it's a moral imperative. But when you think about it, many of these types of existential threats are actually already being translated by policies and incentives and things like carbon credits into economic incentives. And ultimately, what really makes us go to space is that it makes economic sense. That's why we do it. Now, when you think about economics, you need to start by thinking about foundations. So I show these pictures here not because I'm going to talk about building an even taller tower, but because I wanted you to embrace something that all of humanity has known for all time, that in order to build up, you need to have a strong base. We knew it in the pyramids, even the most recent structures are embodying that fundamental idea. Children with blocks have the same idea in their heads, or they learn it quickly. Well, let's look at where we are in terms of our thrust up and towards space. We have a strong base down here where we have skyscrapers and air traffic which hold many, many people off the surface of the Earth already today. But then above that, we have our space industries with a big gap in between. And the space industries support a little bit of science above that. How do we get there today? We get there with rockets. I want to talk a little bit about that foundation, and I want to talk a bit about rockets. So let's start with the foundation. In our foundation today, we've got skyscrapers. They do very well. They put people in these buildings because it's prestigious, people don't turn over, it saves them a lot of money in their companies. That's the fundamental reason skyscrapers are built. And it's a very big business, it's successful. Airlines are similarly doing very well. Right now they support over 700,000 people in the air above us at any given time. And the airline industry has made recently over $700 billion of profit per year. And you think about it, you divide those two numbers out, you end up with the space that you take up when you're sitting in an airplane, on average that's worth $1 million a year, that little bit of floor space. Well, how about rockets, the thing we're using to get across that gap we have right now in the pyramid? Rockets started out strong. The red in this diagram is the failed launches. You see they've come down over time, and the green is the successful launches. You notice though that since the 90s, they've been kind of trending downwards. Now if you look at human spaceflight, it's a similar kind of story. In the 90s, it peaked. In the 2000s, it started coming down. In 2010s, we're even lower. If you project to the end of the 2010s, we're probably going to be around half of the number of humans being launched into space as we had in the 2000s. All right, so let's look at this diagram some more. What we really need to do is build something in here. If we do that, our space industries can start to grow on that foundation, and of course our space science can grow on that foundation. But the question is, what do we put in here? And what are the criteria for something that belongs in there? Is there a precedent for this? We already have perfectly good rockets taking people into space. There is. There were perfectly good ferries taking people across the English Channel and across many bodies of water between land and islands such as Prince Edward Island. But they went ahead and they built the channel anyway. In fact, they've been wanting to build the channel since the 1800s, and they only recently did it in the 80s. There's lots of large infrastructure bridges that replaced ferries over the time. So when people invest, they think long-term when they build this kind of infrastructure. Similarly, trains got replaced by highways, elaborate highway systems over the years. And more recently, this is an interesting one, even airplanes are being replaced by maglev projects. So Tokyo and the corridor in California, for example, 2 places we're talking about building maglevs to replace routes that are dominated today by airline traffic or cars. All right, so this brings us to the audacious question. Ferries that are bridges as rockets are to what? So they got to look at that space again and think, what are some criteria in the space of things that are going to place rockets? Well, if we're going to build a transportation infrastructure, it needs to offer a premium service or some kind of cost savings or some convenience perhaps, or at least be a secure investment. If you think about building a tourist destination in that space, well then there's a lot of criteria such as it has to be safe as a skyscraper. It has to be fast and convenient to access. It has to expose us to acceptable levels of cosmic rays for tourists. When you go someplace, you need a destination, some stuff to do up there. So it needs to be like a bit like a Vegas or a Dubai in terms of its entertainment potential. I'm going to take a little side here and ask you guys if you've ever been to Waikiki. Has anybody been to Waikiki? Yes, a few people? Do you remember this pier in Waikiki? No. Okay, how about Santa Monica? Has anybody been to Santa Monica? Do you guys remember this pier? Yes, people remember the pier in Santa Monica, right? Now the reason you remember the pier in Santa Monica is because there's stuff on it to do. There's a place to go. When you build a bridge into space, it's effectively a bridge to nowhere right now, at least from an investor's perspective. We see lots of places to go, but investors think about it and they go, there's nothing up there. Why would you want to go there? So you need to build a destination at the same time you build a bridge, kind of like the Santa Monica Pier. And you need to compete in general when you build these things with amenities that are in other tourist destinations. All right, next criteria is about space access, our favorite topic. So if you're going to build something in here, we need to support a major industry, at least one disruptive new space industry. And that could be beamed solar power, it could be asteroid mining or mining the moon. It could be a major space settlement initiative. There's lots of possibilities, but it needs to support that, which means fundamentally it needs to bring launch costs way down. And as a mitigator of those existential threats, you need to be able to show that you can do things like monetize carbon credits, or reduce the rate of fossil fuel consumption, reduce the proliferation of weaponizable technologies, or make it affordable for lots of people to emigrate to space. These are some criteria that would say, hey, you've got an idea here that has legs. And last but not least, in terms of criteria, it needs to be technically feasible, and it needs to be economically feasible today. What can do all those things? Well, when investors look at all the existing proposals today, and there's things like space elevators and these inflated towers and launch loops and all kinds of ideas. When they look at them all, they say, no, none of these meet the criteria. And they just cross them all off and they don't get any investment. And the reason they don't get any investment is quite simple. Any investor, take a napkin and do some napkin math. They figure out what the business potential is. I looked at how much material is actually in space. This is all the material is being tracked by the Space Surveillance Network. And then I also wrote a Python script to actually tally up all the launches over time by all the countries and calculate how much payload has actually been launched into space. And that's this little red dot up here around this time frame. So it turns out that if you do this kind of analysis and figure out in the time frame you want to build your space infrastructure, what the total amount of payload is that is going to be going up into space in that time period. And so in this case, I chose an example of 2025 to 2038, which might be an investment window of interest. And I figured out that about 4,480 tons, or metric tons, are going to be launched into space in that time frame. Now, if you're an investor, you say, okay, what's the current launch price? It's $10,000 per kilogram. So you do some math and you say, oh, it's $44 billion worth of business right there. That's pretty good. But then you scratch your head and you say, well, that's where I break even. I got to make some profit. So I really want to be like a third of that in terms of my investment. And then on top of that, you hear the story about some guy named Elon who's going to launch stuff for $1,000 a kilogram, and you're like, well, maybe I should readjust my numbers. So now you're kind of getting down into the like $1 billion worth of investment, if you think like that. And you think, oh yeah, there's also, so this market's already being satisfied by lots of companies that build rockets. So I'm only probably going to get a small chunk of that market. And suddenly it seems really unattractive as a business investment. So that's where you need an audacious idea to solve the problem. And this is what this is, tethered ring. So I'm going to show you a quick video. This was made in Unity. And And there's no soundtrack, I'm sorry. I can hum though. So the Earth protrudes through this pipeline that's been built in the ocean, and these stays are attached to the surface of the Earth on the protruding side of the Earth, and then tightened up, and they actually pull the pipeline, this big circular pipeline ring, they pull it away from the planet. And the reason that the ring doesn't collapse is that inside the ring there's an internal mass stream, or essentially a second ring spinning around about 2 or 3 times an hour, and it's on a maglev system, and it creates an inertial force. It's outwards. And I'll show you in a minute how this all works. Before I do, I want to kind of explain that there are these small space elevators you can use to ride up to it. So it does use space elevator technology. There'll be a marine node, as they call it in space elevator business, where you get on the bottom of the elevator and you ride up to the top. And it's about 30 to 50 kilometers up to the top. And once you get to the top, there'll be transit systems you can use to get around on the top. Okay, so in order to draw these pictures before and make them visible, we had to make all the dimensions larger than they really are. In practice, the dimensions of these cables and rings are very fine. If you were looking at them from the ground, they would look like spiderweb would look like from about a meter away. So very, very thin. They'd glint in the sun, but you wouldn't see them as substantial objects. Imagine we build around Antarctica. There'll be that moving ring I talked about will spin around inside the stationary ring, and it'll generate inertial forces. So looking from the side-on view, those inertial forces will be outwards, like here and here. We're going to zoom in on the side, and we're going to zoom in some more and look at what that really looks like close up. So we have that inertial force I just described, and it's going in this direction. The force of gravity is towards the center of the planet, and the cable is attached to a point on the Earth here, and it's generating a tensile force that's in this direction. And these 3 forces are all going to add up to 0. Which essentially means, when they add up to 0, means the inertial force plus the tensile force of the tether create a vector that offsets the force of gravity. And that's what keeps it up. Now you can build this entire structure in the ocean on Earth just by laying pipeline with pipeline ships. You don't need to build it in space or anything. And after you finish building it and you speed up that internal ring, you can actually lift it into space by tightening up the tethers. So that's a major advantage of this technology over other technologies that have to be launched into space in order to become viable. They need an existing space infrastructure like heavy boost rockets, which are expensive to get them up.
I just got to pause it here and say something, everybody. Does this not look like the black ring with the sun and the darn clock arms that we just saw pointing at 5:30 over Mount Diablo? Let's continue.
Which makes their cost prohibitive. This is an actual simulation based on the physics. And you can see that the ring here starts off on the ground. It looks like a side-on view and goes up. The tether is being unwound from the back of a ship, which travels towards the South Pole and pulls it up. So from the ship's perspective, it's kind of like launching a kite. Each one of these tethers is being pulled in as the ship moves forward, going kind of backwards away from the ring, and lifts it up. Now, by the magic of PowerPoint, I can turn this video on its side. So imagine there's a ship right here pulling that black wire, which is the tether. So it's pulling the tether away from the ring, and the ring is going to go up into space like that. Here's a close-up of what it looks like. In reality, we need more than one ring because of redundancy. We need to be able to take one offline to do repairs, and we also have to be prepared in case there's some sort of accident. So we have 5 rings in our plan, really, which are these objects here. And then we're going to have habitats up there, and we'll have a maglev system that travels around the ring so people can get between the habitats, or also travel between terrestrial locations or population centers on Earth. And there's a few more details I want to quickly go through. Solar powered. There'll also be hydrogen being pumped up there as a backup system. The ring has to be mechanically isolated using pistons or something to separate it from the rest of the facilities. And the structure will be stabilized aeronautically, so that we're still in a little bit of air. There's a rarefied atmosphere up there, and that atmosphere can be used to refresh the air in the habitats, but also to provide a means of doing aeronautic stability control to keep everything where it's supposed to be in the event that there's winds or storms around. And of course, we're going to need a large army of robots and drones up there to inspect and maintain this stuff, because it's in the upper atmosphere where people can't breathe. I want to talk a bit about how one finances this audacious idea, because that's the key to this technology, is that it's financeable. It actually makes economic business sense. So let's start. The idea is to build it in the largest part of the Pacific Ocean, which is here, and then shift it over the population centers in the Pacific Rim. So now you can serve places like Sydney, Japan, Hong Kong, you got a little bit of China there, a bit of Russia there, the western coast of the United States, even New Zealand is serviced by this ring. So that's a large customer base. If you look at what's going on in the airline industry right now, this is a picture of all the airplanes flying around that area. There's hundreds of them at any given time servicing these population centers. Now what we want to do is build basically a maglev transit system on the ring that can take people around the ring to different destinations and bring them up on elevators and take them down on elevators. Maglevs are already becoming a new form of transportation. We're seeing Tokyo is investing lots of money to build one. Elon Musk has talked about building the Hyperloop. We believe that in the future there'll be an interconnected network of these maglevs, and we want to build one that's up in the stratosphere around the Pacific Rim to serve that market and compete with the airline industry. So let's look at how this would work. If you had a passenger going from Sydney, for example, to Los Angeles, that's the trip that you would take in the stratospheric maglev, and then this is the trip you would take in the airplane. And these are the basic numbers. So the airplane trip is much slower because it has to travel at subsonic speeds, whereas the stratospheric maglev is up in the atmosphere where, well, the upper atmosphere where there's only 0.1% air left, and it's possible to travel very quickly there. So you get a much faster trip. So there's many advantages to the stratospheric maglev idea. Unlike traditional maglevs, which cost a lot per kilometer because they're supported on pylons and they have to get land usage rights, this one's away from land and is supported by tension of cables, so it's much cheaper to support it, and that makes it much cheaper per kilometer. You're so high up that it's much cheaper to maintain the vacuum compared to, say, a Hyperloop type idea. And you're above the reach of terrestrial threats, such as weather and seismic activity up there as well, so that's an advantage over some of the airlines and things like that. But there was one big question we had, and that was, if you're up near the edge of space in this transit system, are you going to expose your passengers to more space radiation than they would be getting if they were on an equivalent airplane trip? And so to answer this, we did a study that was actually sponsored by NASA Hackathon. And our study was to figure out, well, basically how much radiation dose the passenger would get if they were in a stratospheric maglev compared to an airplane. So we got some data from NASA, and we extracted it. We had some clever guys doing that. And we came to this interesting discovery. And I've shown up here a picture which actually comes from some student work that was done in California. So if you're from Bishop, California, or anywhere near there, you should give yourself a little shout out, because that was pretty cool. These guys did balloon studies, and they produced some data that's actually been supported by more rigorous scientific articles. What this graph is showing is it's showing the radiation you get versus essentially its time this balloon was flying. But the time the balloon is flying is kind of equivalent to the balloon's altitude. I'll show it in a minute. It goes up to this point here, and then it pops, and then it comes down. What they discovered is as the balloon goes up, obviously the space radiation goes up as well. But then it reaches its maximum around here. And then space radiation starts to come down again, even though the balloon is still going up. And think, why is that? You would think the radiation should continue to go up and up and up and up and up to get into space. Well, it turns out that the way cosmic rays enter the atmosphere and they explode and shatter and make a fiery wake of additional subatomic particles, that actually causes an increase in radiation at lower altitudes than you get at higher altitudes. So there's this thing called the Pfotzer maximum, which is a place where the radiation is at its most intense in the atmosphere. And above that, you get less radiation, which I thought was very interesting. Now, airplanes typically fly around here, and our structure is going to be up pretty much where the balloon popped, up around here. So there's actually slightly less radiation if you're in a stratospheric maglev than if you're in an airplane, which is interesting. But we continued our study, and we also discovered it's much better than that, because if you think about an airplane, it goes up, flies, comes down, right? Stratospheric maglev, you go up even higher, but you come down earlier because you take your journey is a shorter period of time. And if you look at the radiation dose in an airplane, well, it kind of goes up steadily for that entire time at a certain rate. And in the stratospheric maglev, it goes up at a slightly lower rate, but it stops going up.
So when you're in an airplane, you
sure.
get radiation
Your total
exposure,
radiation
everyone.
dose in a stratospheric maglev is actually going to be significantly less than it would be if you took the same airplane trip. And you've got all the bases covered on this idea in terms of why it makes sense to do this. And so our conclusion was it was a great idea. It's clear that maglev technology is poised to take on the airline industry. It's clear that it can travel higher and faster than a commercial airliner and therefore offers premium service. And despite its higher altitude, your radiation exposure is at least 50% less, maybe as much as 30% of the airplane trip. You get the shorter travel time, you're above this radiation limit, so your radiation dose is lower. And also, because you're a maglev system, you could automate a lot of the service. You don't need as big a flight crew, and it's a shorter trip, so you don't need as many staff. And so overall, your staff costs are going to go down, and your staff, which is radiation workers, by the way, their exposure is going to go down as well. So it makes it much easier to run this business. So we got here as a great idea, and the question is, how much money does the transportation industry have to throw around, and can that be useful for funding this? So let's look at some things that the transportation industry has spent money on lately.
So let's just stop, and let's just go back. I know it's very interesting. Can't believe I'm not saying anything about a lot of stuff this guy's talking about, but this is what I believe. I think this is being built up there now. It's either completed or they're building it right now. This is what's being built. This tether line, and there's been videos of people like on the ISS feeds
Get on the bottom of the
where people are like, what's that line going across the earth? It's the tether line, everybody. It's the main line, and the main line and these tethers, and you heard him, the ships pull it along, and so forth. Now the elevators that he's talked about, I don't think are there yet. They might be. There might be some. Okay, there might be. I don't know, but from what I'm seeing on this and what he's showing and what we have seen and others have seen.
Here's a close-up of what it looks like.
This makes a lot of sense. Okay, for no wonder they're blocking. No wonder they're trying to cover all this stuff up, everybody. Now, how long has this been going on and they've been building it? I don't know. This video was put up last June. I think they're building it. Now, for another something to just keep in mind, history repeats itself. You gotta be careful. Right? History will repeat itself if you don't learn from it. Well, the Tower of Babel, wasn't that something about they tried to build a tower to God or something like that, and God was like not having a part of that, and so boom, everybody's had a different language and nobody could understand everybody. Well, this is gonna cause God's wrath even faster if what he's saying, we've already got the skyscrapers, we've already got the space stations, now all we got to do is connect them. They trying to build something all the way up there. Didn't they learn This is going to bring God's wrath even faster. Don't be trying to build a bridge, a tower from the earth up to the heavens. So there you have that rabbit hole. But this tether line, this stuff, it's. I think they're building it now. I think they're building it now. Everybody, God is good. God bless.